Hello and welcome to the sixth in my series of videos on second order systems, short videos on second order systems. We will pick up where we left off. What we're doing is we're making a model of this system of which we see the response here. And we've picked the performance parameters off of this response. This is a unit step response. And we've determined these parameters, and we're the three parameters that make up a second order system. And we have determined K to be 3 because we put in a step of 1, we get a response of 3, so the system has a gain of 3. Then we looked at the overshoot, and from the percent overshoot, and from the percent overshoot we were able to get zeta. And then we looked at the damped oscillation, and from the damped oscillation we were able to get the natural frequency, omega n. So now we know those three parameters, and we figured those out actually using an open source program that's a lot like MATLAB called Octave. And as we can see here, that our K is 3, zeta is 0.919620, and omega n is 4.9290. So we can actually make a transfer function of that, and the way you do that, the way you put it in there, there's more than one way to do it, but the most graphic way to do it is you identify first the variable s as a special figure, or special character, I guess you would say, for making transfer functions. Now, I know when I do this I'm going to get a mistake, but I want to show you how to get out of that. The problem is that this function, this TF function, is part of a controls package that goes with Octave, and we haven't loaded it. But they're nice enough here to tell you how to do it. What you can do is issue the command package load control from the Octave prompt, and that will load the control package in that we can use. So pkg load control, voila, it's loaded. So now we can go actually issue that command that we had before, and you don't even need to type it in. You can hit the up arrow twice, and here's the function that I was trying to put in, and this simply identifies s as a special character. Now I'm ready to go. So I can put in, let me collapse, or not collapse, but make smaller Octave, and then our transfer function for our second order system, I believe, let's see, I've given it somewhere here. Oh, well, there it is, but yeah, I could just put it in like this, but I think also I did this with my Word file. Oh, here we go. Yes. There's our second order transfer function. Let me just get this up here so we can see it. So go back to Octave. Here's Octave. And so what we'll do is we'll put in g second equals k times omega n squared, that's the numerator, divided by s squared plus 2 times zeta times omega n times s plus omega n squared. And if I issue that, you see that I get this a result here. These numbers were calculated because omega n squared is going to be this number, and then this number here is 3 times that number because it's 3 times k times omega n squared. That's omega n squared, and actually it looks like it's correct in that this is 3 times 24.3. So now we have this model named g second, and we can actually produce the step response from here by issuing a step command, step, and then you just put in g second. And it's going to put a unit step into this transfer function and produce a result. And there it is. And this looks like our curve. Let me come back here and then go to Octave and pull that curve back. I'll tell you what, let's first go to our curve. There it is. And then pull the Octave curve back up so that they're close to each other. Maybe I can make this one a little smaller. And then if I make this one a little bigger, we can compare those two. And it does indeed seem like if you look at various features, like for instance this curve right here looks like it's crossing 1, or let's see, this is 3. So it's crossing 3 at 1. If we look back over here, it's crossing 3 at 1. Of course, this goes up to 4.6. And we can actually zoom in here, I believe. I thought there was a way to actually get that, but we can just blow this up. The problem is that this curve is really kind of what happens in a simulation is it simulates at various time slices and then draws straight lines in between them. And here what we've done is let's see, I can pan over here. It goes from the time steps in the calculation look like they're going from, let me make this a little bit bigger. This didn't help a whole lot. That's 0.4, that's 0.6, that's 0.8. So they're jumping quite a bit, and we need smaller time steps is what we need. So what we can do, let me scale this back out. We can go back to Octave and actually issue that step command again. I looked at how to do this before, and let me see if I can remember how to do it. What you do is you put in, let's see, let me look it up. Let's see here, step command. So I'm just over here on my other screen, and I'm entering GNU Octave step function. And actually the other thing that I can do, I believe, let me try it over here in Octave, is you can say help step. And then it'll come up with a whole a different option. So what we're going to do is we want to be able to put this DT function in right here, which is, I read about this before. It's the time steps that you put in. So you put in the system like we did before. You put in the final time, and if we look at our an original simulation, it was 5.5 seconds, so we'll put that in. Okay, let's get this back up again. And then you want this DT, so we put in Y, T, and X that are fed back to us. We don't, yes, we do need to do that. Or maybe we don't. Maybe we can simply put in these three arguments. So this is our system and the final time and then DT. Let's try that and see what we get. We may have to come back and put these arguments in, or these things here on the left. But let's try it and just see what happens. So step. We want to put in G second. That's our system. Final time is 5.5. And then DT, let's make it 1/100th of a second. Now let's see if this produces a result. All right, now we go look at our figure again. And indeed it did. So it smoothed the curve out by putting in that differential time step. Now we can zoom in. Let's see, what's this? Oh, that rotates. I don't want to do that. So we can, oh, this is nice. So I can now circle that. And if I look at that, hey, it went exactly to 4.6. Well, we calculated the overshoot correctly so that it would go to 4.6, and it did do that. All right, let me auto scale this again, and we can compare that with the original figure. Let me pull it back up again. There it is. And indeed, they are they have the same. Actually, what I could do is I could probably make this like the right, shrink it down so it's almost exactly the. It sits almost exactly on top of it. So we go up to 4.6. I might actually be able to put a better grid in here too. I'm not sure, but let's don't worry about that. It comes back through and it goes through 3 at 1 second, just like that does. It goes up, and the second peak is, let me pull this up a bit, is a little bit before 2. The second peak here looks like it's a little closer to 2. So what may have happened here is that the omega n that we put in is a little bit high. This comes from actually, well, what we did remember is I guessed at the peak time here, and perhaps what I did was I guessed a little bit slow, so that we wound up with a slower omega n in our model than we did here. But it's very slightly off, and you could actually go fix that by changing omega n and reducing it and then running the model again. So you could tune this by excuse me, going back and adjusting the parameters that looks like they may be causing a problem. Our overshoot is perfect. If this is 4.6, it looks like our omega n is a little bit long, so we could actually go in and just by trial and error you could reduce omega n by what, 5% and see what happened there, or increase the omega n, because that's the speed, and see how it worked. But anyway, we're really close to the result that we wanted. Okay, I'm going to stop here, and we will have another video on how to make a model to get the same result in Modelica.